there, Algebras. Welcome to your Chapter 14, Lesson 5 notes, all about exponential regressions. So this will actually be pretty easy for us because we've already been talking about linear regressions. And now we're just going to look at data that instead of when graphed on a scatter plot, forming kind of a line pattern, now it's going to form more of an exponential pattern in the data. Okay, so the data that we're going to start by looking at is coffee data, right? So we're looking at cooling temperatures from a freshly brewed cup of coffee. So when it starts being brewed, the pot is approximately 180 degrees. So at 0 minutes, we're at 179.5 degrees Fahrenheit, right? And then the temperature of the coffee continues to be taken for the next 50 minutes, and we can see where we're heading, right? So what we're going to do is first identify which of these things is our X variable or our independent variable, which would be time. And then time in minutes. And then we are going to identify the dependent variable. That would be the temperature of the coffee. So this is our Y variable or our L2 variable. So this would be the temperature. And we are in degrees Fahrenheit because, well, we're in America and we have to be different from everyone else. So we go Fahrenheit instead of Celsius, right? So what we're going to do now is we're going to enter these things into our lists. So let's grab our handy dandy graphing calculators. And here is mine. What I'm going to do is I'm just going to move this so that the data is still visible. Obviously, you have yours on your own paper, but here's my calculator. And we are going to start by let's clear our RAM to make sure that there's nothing in our graphing calculator that's going to be a problem. So second and plus sign gets us to our memory. Let's go to 7 for reset and just press enter 2 to reset our RAM. That just means that if there is any data in my L1, L2, it's gone now. If there were any scatter plots or stat plots, they're gone now. If there was anything in my Y equals any functions, they're gone now. So now I can press second and 0 to get to my catalog, because now that I've reset the RAM on my graphing calculator, I have to turn my diagnostics back on. So let's arrow all the way down to, I went a little too far, diagnostic on, and then press enter, enter. All right, now our R values will appear when we run a stat plot on this, right? So now, finally, we can enter our data. Stat, enter. In L1 is where we're going to put our time in minutes. So 0, 5, 8, 11, 15, 18, 22, 25. Do I really need to keep saying all this? You can read your data, yes? Okay. Let's just double check. This says we've entered 14 data values and it is now asking for my 15th data value. Let me double check. Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 data values. Perfect. So now we arrow right to L2, and now we're going to enter our temperature of our coffee in L2. So 179.5, 168.7, and you can, of course, press enter to keep going as you continue. Oops. And notice I'm kind of checking myself as I go, looking back and forth at my data as I'm entering. When I have the physical graphing calculator, it certainly makes it a bit easier on me. But since I'm using the computer one so that you can see all my moves, It takes a little bit longer to enter the data. So take your time, make sure you're entering the data properly. That's a big deal. You need to analyze the correct data. And one of the things that is a very big deal when we're talking about two separate variables of data is that L1 and L2 have to line up because each of these is a point on a scatter plot. It's an X and Y coordinate on that scatter plot. It's the time and that temperature that they match up. They need to line up. So notice at the end, I needed to make sure I had 14 in L1 and 14 in L2, and each actually matched through the chart. Okay? So that stuff is a very big deal. Now that we've got all that done, let's actually make a scatter plot on our graphing calculator. Okay, so what I'm going to do here is just make my graphing calculator even bigger for the time being so we can really see what's going on that scatter plot. Okay, so there we go. Let's press second and y equals. And this takes us to our stat plots page. Press enter and enter again to turn plot 1 on. Now the beauty of this is type 1 under my stat plots is a scatter plot. So if that's what I want to make, it's already highlighted. The other great thing is I did put all my X values in L1 and I did put all my Y values in L2, so I don't need to change anything below it either. Actually, all I need to do is make sure that I'm not looking at a standard XY coordinate plane. I need to look at a correct quadrant 1 with a good scale for the data I have. So I press zoom, and notice we've got zoom stat down here, number 9. So you can either arrow down and highlight 9 or just press 9. And notice there's our data nicely plotted for us. Boy, that does look like it has a bit of a curve to it, doesn't it? It doesn't look like a straight line this time, all scattered around a straight line. It doesn't look like that. We can see the visible difference this time. Okay, so let's get a proper regression so that we can predict the temperature of the coffee, say at 60 minutes, an hour, right? After an hour of the coffee sitting out, like, this one. So let's press stat, arrow right to calc, and let's kind of look at our options. We know number 4, our linear regression, is what we have worked with previously. When our plots along our scatter plot look linear. But we noticed a curve. We can see a curve in that data. So instead, let's kind of arrow down our list. It did not look like a quadratic. It's not a U shape. It did not look like a cubic. It wasn't like that vertical snake. Does not look like a quartic. Linear regression, we already knew. LN is actually a logarithmic regression, an exponential type regression, but not the same direction we're looking for. We want 0, exponential regression. So you can either, from now on, when we get to this screen, press 0 or highlight 0 and press enter. Notice our X list should be L1, our Y list should be L2. We can always change that if we need to, but again, we used that, so we're okay. We don't need to change that. But where I want to head down is the store regression equation. So arrow down, so your highlight is in store regression equation. And now follow carefully. VARS, VARS, arrow right to Y VARS. We want the function, so 1 or enter. And then Y1 is perfect, 1 or enter again. What this is saying is whatever that regression equation comes out to be, please put it in my Y1 for me so I don't have to do that. That's what this part is doing. So it's actually a really good piece that the graphing calculator can help us with. And then finally, we can arrow down to highlight calculate and press enter. And notice because we turned our diagnostics back on, we get our R value as well, which is a pretty darn good R value. So we know that our initial value, okay, for this is approximately 171.46. We have a continuing decimal, but that's enough. Our B value, meaning our base, is approximately 0.988. And we know from our exponential functions unit that this means we have a decay, an exponential decrease function, because this is a value less than 1. Then, of course, we know from previous work with regressions that having an R value of 0.98 is a very good fit for our data. So this exponential regression is a fantastic fit as X increases, Y decreases. That's what the negative piece of it is telling me. So what's going to be really great is when I press graph to see that exponential regression with my data. And I can see a pretty decent fit with my data. All right. It's a pretty decent fit with my data. Okay. So now, next step, let me just make this a little smaller again. Oh, sorry about that. Make this a little smaller and kind of put it out of my way. Now, we want to write down our exponential regression using our data, right? And we want to copy our graphing calculator screen because, again, we don't know which of these decimals is going to be important. So let's make sure we have that whole deal. So second and mode quits back to our home screen. If I want to get back to an entry I just put into my graphing calculator like I do right now, press second and enter. And notice this is the exponential regression that we just did. We wanted our X list in L1, our Y list in L2, and to store our regression equation in Y1. So I'm just repressing that so I can get my data back up on the screen to copy it on my paper. So we know that we have Y equals A times B to the X power, where A, our initial value, is 171.4617,283. Our B value is 0.9882469577. And our R value, we can still skip R squared, and we're just looking at our R value in general, is negative 0.9849556976. So copy that down all the way. And this is that exponential relationship between the amount of time that has passed since the coffee was brewed and the temperature in Fahrenheit of the coffee at that time. Okay? That's what we're writing down. The next thing I want to do here is create that regression equation for myself where I round. This particular question does ask me to create that regression equation rounded to the nearest thousandth, which is 3 places behind the decimal value. So let's take this and create our own regression equation with the rounding. Y equals 171.462 times, this is where the base comes in, 0.988 raised to the X power. And that regression equation is slightly different from the one that we have here where it was not rounded. So what I want to do right now too is press Y equals. Notice right now my Y equals is showing me that I have a stat plot on and that this is the regression equation that it entered into my graphing calculator for me. But what I want to do is in Y2, I want to enter this one. So 171.462 times 0.988, end parenthesis, raised to is the caret button, X power. Actually, am I taking a sec? Let's just graph it real quick. Oh, they're pretty darn close, aren't they? So even with that rounding, they're pretty close to each other as far as the two equations go. All right, even with that rounding, and still pretty good fits for the data. Okay, just wanted to take a sec to take a look at that. Now let's look at this question that is this famous lawsuit that everyone always kind of looks to. There's a famous lawsuit against McDonald's where a woman had ordered coffee from McDonald's and had accidentally spilled it on herself in her car after she got it, and she suffered some very serious burns. And she was actually awarded $2.7 million for burns caused by 180-degree coffee that spilled on her lap in her car. So now most food service businesses, because of this, only allow coffee to be 155 degrees when they actually give it to a customer. So using our graphing calculator tables, and we're going to use both tables. So this is why I put both equations into my graphing calculator. We're going to find the amount of time in minutes it would take for that coffee to be servable. So let's say I'm a worker at McDonald's. I brew a fresh cup of coffee and someone comes through my drive-through line and asks for coffee. I've just brewed this fresh batch. How long do I have to wait to serve it to someone who orders it? So let's take a peek. Let's make our graphing calculator a little bit bigger again. And let's press second and graph to see our tables of points. Okay, so let's look. Oh, all right, our y-intercepts are pretty accurate. Some changes here as we go down the line, but we're looking for where do we have less than 155 degrees, right? So let's take a peek, kind of look down the blue line, and oh, we get 155.99 here, and then 9 minutes right here, we've got less than 155 degrees, right? Because we can't go this is still greater than 155 degrees. Can't serve that. Got to serve a little bit less than 155 degrees. So at 9 minutes, we see that for both of our regressions, both our original and our rounded one. That's awesome. That doesn't normally happen. Sometimes the rounded one does give us different information. And if you look at 8 minutes, one is saying 155.9 and the other is saying 155.6. So they are slightly different, and depending on where I would need to round or what value I'm looking for, I might have a different answer to this question, as you can see. Thankfully, both regression equations this time give me the same result, which is I can serve this coffee after 9 minutes. Okay, I can serve this coffee after 9 minutes. It's going to take that long for the coffee to cool down so that I can serve it. Okay, less than 155 degrees. Gotta be. All right, next question. Scale our calculator down again. Get on to the next question. Now compare the rounded value. Are they the same temperature? Not exactly, but close. And that's why we wanted to look at both, because they're not exactly. And if we're trying to get to other values, right? We're trying to look at some other values, we can see down the line they are changing their paths, right? We can see that they're going a little bit away from each other as the minutes increase. So speaking of, we want to know how many minutes it's going to take for the coffee to reach approximately room temperature, which is 76.4 degrees. So let's keep heading down the line. I'm going to go on my X's because that's, of course, my time. And as I'm heading down my X's, just look at my Y's. Now we're still in the 140s, so this is going to take a bit. Heading down our X's, we know from the data that after 50 minutes, we're still at 100 degrees. And we're trying to get to 76 degrees. So, I can kind of increase this push down a little bit further. Okay. So we can see, okay, all right, getting better. We're trying to get to 76.4 degrees, classic room temperature. And I'm still in the, oh, look, I depart from the 80s quicker in the red column in our rounded exponential function equation than in our other column, our blue column, which had all of, oh, and here we are. Look at that. We do have a difference this time. So see where the rounded version does make a difference. If you're going with the version of our exponential function that has all of its pieces, we get below room temperature, at or below room temperature at 69 degrees, or excuse me, 69 minutes. So 69 minutes with the original regression equation, right? But if I'm looking at the rounded regression equation, we get below 76.4 at 67 minutes. So notice as our X value increases, the deviations away from each other start to increase with our original regression equation versus our rounded regression equation. So what you're going to want to do is be careful if the question specifies one version of the equation over the other. Okay? You want to be very careful about that. Now, we did not have a specification in our question, so we got lucky. We could accept either answer, right? There wasn't a specification. But we need to make sure we read carefully to make sure there's not a specification of whether we should use the original or the rounded version. Okay? So just be kind of careful about that. All right. So I want to see the next one, which is what's the temperature of coffee that's been sitting out for an hour? Well, how long is an hour? It's 60 minutes. So I need to make sure I look up at an X value of 60 and then look across. Okay, so for our rounded version, and I'll continue putting the rounded version in blue, we have 84.4 degrees. And for our non-rounded version, or sorry, this was the non-rounded version. For our rounded version, we have 83.1 degrees. So do be careful which one you're being asked for, right? Original or rounded. And then how about coffee sitting out for 2 hours? Well, if 1 hour is 60 minutes, 60 times 2 is 120 minutes. So we got to scale way down, right? Now notice I'm just using my arrow to go down and I just kind of held it for a little bit. But you could also change where your table starts from. So if I look across, we have 41.5 degrees or 40.3 degrees. So 41.5 degrees versus 40.3 degrees. Now, let me ask you, realistically, is that going to happen? Because your room is not going to go to 40 degrees. Is your coffee really going to go that far? No. So there is kind of a time limit as to when your regression equation is realistic. Your room is not going to go to 40 degrees, so your coffee is not going to end up going to 40 degrees. Unless, of course, you're a cheapskate and you just have your heat off in general. So, that's what happens. All right, so real quick, let's go over our regression equation, or excuse me, our R value. So how good is the fit of this equation with our data? So what's the possible range of correlation coefficients? So as we know, it's from -1 up to and including +1. -1 is a perfect negative relationship between the two variables, while +1 is a perfect positive relationship between the two variables. So what constitutes a good fit? Kind of plus or minus, I would say 0.75 for an R value. Lower than that, you really are kind of getting into sketchy territory as far as a good fit. We are going to learn more about more things that can help us determine a good fit for our data. What is the correlation coefficient for this data? So I'm just going to review that R equals from our previous, and I'm going to round to the third place. So our previous R value is -0.985. And I'm rounding this time because we did already look at the full version with all of our decimal values. So this time I am rounding because, again, we're looking at pretty decent R value here. Is this regression equation a good fit? And I would say based on this R value, this is a strong negative correlation. Based on this R value, this is a strong negative correlation between the time increasing and the temperature of the coffee decreasing. Okay? And how will I explain that? Because -1 is a perfect negative correlation. Zoom out just slightly for you. Between our variables, a correlation of negative 0.0985 indicates a strong negative relationship. As X increases, Y decreases. This is indicating a strong negative relationship. Okay? And there we are. Exponential regressions, not that much different from linear regressions. Not that much different at all. Okay, we need to watch whether or not we're being rounded. We need to watch what we're being asked. We can make inferences using our regression. Okay, they're not exact, but they're inferences based on whether or not there's a good relationship. Okay, so the strength of the relationship does help me indicate whether my inference is strongly acceptable or not. Okay, guys, have fun with this. This data stuff is really fascinating and fun. This has been your Chapter 14, Lesson 5 notes. Good luck on the homework, and let me know if you need any help. Bye, guys.